Hi everyone. So we've already learned that the nucleus is responsible for creating nuclear energy. I should say changes in the nucleus as they become large and they become unstable. They attempt to stabilize by basically kicking out neutrons. And so when this happens, you get a massive amounts of energy, also known as radiation. And radiation can occur in three different ways. So let's look at those. First of all, radiation, there's three types. You've got alpha particles. And this just simply means that as the nuclear reaction occurs, it puts off these three different types of radiation. One of them is known as alpha particles, and there's the symbol. One of them is known as beta particles, and there's the symbol, and the other is known as gamma, which we're all very familiar with. Radioactivity refers to the spontaneous emission of particles or high-energy electromagnetic radiation from the nuclei of unstable atoms. This occurs due to the disintegration of the atomic nuclei. That's what we call nuclear decay. It is disintegrating or breaking down. So it either emits, the energy that emits from this nuclear decay either comes in the form of waves or high-speed particles. So the different types of radioactivity are alpha, beta, and gamma, which are classified according to the charge of the electromagnetic waves that they give off. Alpha rays carry a positive charge, beta rays carry a negative charge, and gamma are neutral. So alpha, beta, gamma. It's important to pay attention to this particular illustration because it shows you that an alpha particle, which looks like a helium nucleus, and you can see that it has 2 protons and 2 neutrons. So an alpha particle can be stopped by a piece of paper. A beta particle, which is negative, can slip right through that piece of paper, but can be stopped by wood or aluminum foil or other similarly less dense objects. And then gamma, of course, can penetrate all of that. And the only thing that can stop gamma waves are concrete or lead. So let's look at each type of radiation particle. The first type is alpha. It's very large particles. Again, it can be stopped by paper. They have a very short range. They're stopped easily. While beta are a little bit smaller. They can travel about 1 to 2 meters, and they can be stopped by thin plastic or aluminum foil or other metals. Gamma is pure electromagnetic radiation. It can travel large distances, and it can only be stopped by large materials like lead or concrete. Let's look at this part, the nuclear equation. We're already familiar with how nuclear equation looks for fusion and fission. But again, this is carbon that is decomposing into a nitrogen and a beta particle. And this is what a beta particle looks like. It is a negative electron, and that's just what it looks like. So the strong nuclear force inside of the nucleus holds the neutrons and protons together. And as long as that force is strong, in other words, the particles are really tight together, then it'll hold together. But if the nucleus gets large, those particles spread out, then you're likely to have some instability and some radiation. So the first type of radiation, again, is the alpha particle. It's very massive. It can't pass through paper. It has a +2 charge, which means that it has an atomic number of 2. It has 2 protons, and then it has 2 neutrons. And again, you can always recognize an alpha particle in an image because it looks just like a helium nucleus. And you can also recognize an alpha particle in an equation because it has the same look as a helium. So the atomic mass is 4, the atomic number is 2, and it's helium. Okay, so it is basically identical to a helium nucleus, and alphas, when they lose particles, so that decreases the atomic number by 2 and increases the atomic number by 4. So what happens is, in an equation, there's going to be some adding taking place and subtracting with the new substances that are created. And we'll talk about that later. So damage from alpha particles, they can be dangerous if they get inside the body, but they're so big that they usually don't. And so they can cause your cells not to function properly, leading to illness and disease. Let's talk about transmutation, because as I told you before, you gain an atomic mass of 4 and lose 2 protons. So that is a process where it actually decays into another element, and that is called transmutation. So when that happens, for example, this polonium decays into a lead particle and, of course, an alpha. And so what happens here is that the mass number decreases by 4, and the atomic number decreases by 2. So this polonium, which had a mass of 210 and an atomic number of 84, then decays into a lead, which has a mass of 206 and an atomic number of 82. And the reason that it dropped by 4 and by 2 is because, bam, there is your alpha particle out there, and it has a mass of 4 and 2. So if you added these back together, you would get your original mass and atomic number of polonium. So again, this is what an alpha looks like in an equation. So notice that you subtract 4 from the atomic mass of polonium, and that 4 represents that alpha, and now you get 206. That lets you know which element you're talking about. Then you subtract 2 from the atomic number 84 to represent again your alpha, and it takes you down your atomic number to 82. If you look on the periodic table, you can see that lead is the element that has the atomic number of 82. So how do I know what element it changed to? Look for the new atomic number on the periodic table, and in this case it's lead, 82. This is what it will physically look like in a physical description. So this is radium, which has a mass of 226 and an atomic number of 88. It breaks down. Of course, it emits an alpha particle, and so now you are looking at an element that it has an atomic number of 2 less. Here's your 2 missing protons here, and that turns out to be radon. So radium decays to radon and an alpha particle, and that's how that process works. Okay, here's some other examples. So let's say you have imaginary X element, and it breaks down into Y and an alpha particle. So whatever the mass was before, you subtract 4, and that will tell you the mass of the new element, and whatever the atomic number was, you subtract 2, and that will tell you the atomic number of the missing element. This again is what we've already seen, a radium breaking down or decaying into a radon and a helium. And again, just more illustrations of what this would look like. If you have radon, it breaks down into an unidentified element and a helium. Then all you have to do is take the mass of radon, subtract 4 for the alpha particle, and that gives you your new mass. And then take your atomic number of radon, which was 86, subtract 2, which that goes to the helium or the alpha, and that gives you your new atomic number of 84. And I can look on the periodic table and see that 84 is polonium. Again, just examples. So you have this unidentified element that's breaking down into thorium and helium. So how can I tell which element it is? Well, I just add the mass, 4 plus 230, and that gives me my new mass of 234. And then I can take my atomic number from my helium, add it to my atomic number from thulium, and that gives me my unidentified atomic number, which is 92, letting me know that it's uranium. Then if you have a thulium and you have an unidentified, it's breaking down into an unidentified element and an alpha. How can you find that? Well, you subtract the mass of the alpha, 4, and that gives you your new mass, 226. And then you subtract the atomic number of your alpha, 2, and that gives you your new atomic number, 88, which lets me know that it's radium. If you have an unidentified element, but you know that it's broken down into lead and an alpha, then you can add your mass of your alpha and your lead, and that will tell you your new mass. And you can add the atomic number of the alpha and the atomic number of the lead, and that will tell you your new atomic number. You look on the periodic table, you see that atomic number 84 is polonium. Okay, so alpha particles are emitted by the bigger elements like polonium, radon, radium, americium, and so they're very large, and they undergo the process of nuclear decay, where they decay into another element and an alpha, and that's called transmutation. Now let's look at beta. Second type of radioactive decay is called beta decay. Sometimes in an unstable nucleus, a neutron decays into a proton and emits an electron. So the important thing for you to know here is that this is the symbol for... Sorry, dog interruption. So this is what it looks like in an equation. That's how you know it's a beta particle, and it has a charge of -1. So beta particles, again, they can be stopped by aluminum foil, and because they're like an electron, they have very little mass. Damage from beta particles, they move a lot faster than alpha, and they can penetrate a lot more than materials or substances than alphas. They can definitely do damage if they get inside your body. Again, here you have this large nuclei, and it kicks out basically this beta particle, and so you get a beta particle and a new substance. So examples of radioactive materials that give off betas are the several different types of hydrogen, hydrogen 1, hydrogen 2, hydrogen 3. And remember, they just have different numbers of neutrons. Carbon 14, phosphorus 32, and sulfur 35. So they're a little bit smaller than the nuclei that emit alpha particles. So this is what a beta looks like in an equation. So if you have an unidentified element, then and it's broken down into bismuth and a beta, then what you're going to do is your mass is going to stay the same. So the mass here will be 214, but you are going to subtract 1 from the atomic number because you're gaining that negative beta charge. So 83 minus your beta is 82. So this is lead on the periodic table. Again, if you have cesium and it breaks down into a beta particle and promethium, then you can see that the atomic mass does not change while the atomic number decreases by 1. A beta particle is a fast-moving electron which is emitted